Hello, today we're going to talk about mathematical linear models, where we're focusing on first order differential equations as mathematical linear models. There is a section in the book 1.3 that goes into a lot of detail about building up the models, and there are tons of examples and material in that section for you to read over just to see how some of these models came about. But our focus isn't going to be on the building of the models. We're going to build a few models and then use those for different situations. So we're going to start in 3.1 here, and we will be solving differential equations based on the models we come up with, okay? You may recognize some of the models that we work with from a college algebra class. However, it is not appropriate to use a memorized solution from a college algebra class in order to answer the questions in this section. Because this is a differential equations course, it is expected that you come up with the differential equation that is needed and then solve it and use any given information to find the parameters of your solution so that you can answer any questions about the problem. Okay? So we're going to start with growth and decay and carbon dating. For all three topics, the differential equation is the exact same. It has the form dA dt is equal to Ka. And what that is saying is that the rate of change of the population that you're working with over time is directly proportional to whatever the population is. Okay, so the whatever the population is going to determine what the rate of change is. And we would be given some information about that population at some initial point in time. And that time could be at time equals 0. Typically, we take it to be 0, but pay attention to what is written within each problem. This particular differential equation is a separable equation, so we typically are going to use the separable equation method in order to solve this. Although I have seen people turn these into linear equations, it's much simpler to just separate and integrate. When we separate and integrate, the intermediate steps that are not showing here and kind of make you think you just go to a memorized solution, the steps are to get all the A stuff on one side and get everything else on the other side. So that means we would get 1 over A dA is equal to K dt. And then we would go ahead and put our integral symbols on and integrate to get the natural log of the absolute value of A is equal to kt plus c. And then we would exponentiate both sides to get that e to the ln of the absolute value of A is equal to e to the kt plus c. On the left, that simplifies to be A, and we'll call it A of t. And on the right, the e to the kt remains e to the kt, but then we would rewrite with a times e to the c, but e to the c is just a constant, and so we would rewrite once again and just say this is c e to the kt. So that's how this answer, this solution form is coming about. But again, I don't want to see a memorized solution form. I want to see the differential equation that you're supposed to start with and then work your way towards that solution form. Okay? Now, in this solution form, if we were to apply the initial conditions, A of 0 equals some A naught, we're saying that when t is 0, A is equal to A naught, which will force us to get the C, that unknown constant, is actually equal to the initial population. And so then the solution for all growth, decay, for all growth, decay, and carbon dating problems, it's going to have the form A of t is equal to A naught times e to the kt, so long as the initial population was at time equals 0. Okay? Other letters might be used depending on the problem you're working with, sometimes depending on the book you're working with. Some books like to use P instead of A. P stands for population. Either one is fine. But be sure to read through examples 1 through 3 in the book. They're all covering different types of growth, decay, and carbon dating. We're going to do an example as well. Our example says that the population of bacteria in a culture grows at a rate that is proportional to the number of bacteria present at time t. This sentence right here, the population of bacteria grows at a rate proportional to the number of bacteria present at time t. That sentence right there is telling me dA dt, that's the grows at a rate that is proportional to, and when we say proportional to, that is implied to be directly proportional to. So we get a constant of proportionality, K, times A, the actual population of the bacteria. Okay, so that's the information from the first sentence. The next sentence says, after 3 hours, it is observed that 400 bacteria are present. Okay, well, that's telling me that the A value, the population value at time 3 is equal to 400. The next sentence says, after 10 hours, 2,000 bacteria are present. So this tells me A of 10 is equal to 2,000. And then here's the big question. What was the initial number of bacteria? In other words, we are being asked to find the population at time equals 0. And so we're going to do a whole bunch of work to figure that out. Let's go for it. Okay, so our first step is to solve the dE. And we know that we could separate that, and that would give us dA over A is equal to K dt. We could put our integral symbols on it, and then this would lead us to the natural log of the absolute value of A is KT plus C, which in turn gives us A is equal to E to the KT plus C. Or, in other words, we have A of t is equal to C e to the kt. All right. Now remember, we do not know the value of A at time equals 0, so we're not going to be making assumptions on what C is right now. We're going to leave C as C, okay? However, we do know that here's where we can use the conditions given. So A of 3 is equal to 400 is one condition given. That tells me that 400 is equal to C e to the 3k. We also know that A of 10 is equal to 2,000. And that tells me that 2,000 is equal to C e to the 10k. Okay? Well, in each one of these, I could solve for C in one of these and substitute it into the other one and see what I come up with. Okay? Now, if I solve for C in, let me see, which one did I want to solve for it in? I would like to solve for C in the, actually, I would like to look at a ratio first, okay? I would like to look at a ratio because what that will help me to figure out is what is K. So the deal here is I don't know C, I don't know K, I need to know both. And so I can determine that by looking at a ratio where I compare the C e to the 10k to the C e to the 3k. So we're saying C e to the 10k is to C e to the 3k as 2,000 is to 400. So we can always look at ratios like this when we're dealing with some of these growth rate problems or decay rate problems. And the idea here is that those C's are going to cancel. right? Those divide out, and e to the 10k over e to the 3k becomes e to the 7k, which will equal, it looks like 5. Okay, and so then we can go ahead and take the natural log of both sides and get 7k is equal to the natural log of 5. So that means k is equal to 1/7 times the natural log of 5. Okay, well, if I know k, then I can plug it into both of the original equations that I had. And I'm going to do something else here real quick. In these equations, the first one where 400 equals c e to the 3k, c would be equal to 400 times e to the minus 3k. And now I know k, so it's 400 e to the minus 3 over 7 times ln of 5. And in the second equation, I could do the same thing. C is equal to 2,000 times e to the minus 10k, which means c is equal to 2,000 e to the minus 10 over 7 ln of 5. These should both give me the exact same number, and they do. They tell me that c is approximately 200.6787642. That's the value I get. Okay, so I know c, I know k, but those aren't what I'm after. Okay, so now let me just kind of put this away here. We have a of t is equal to approximately kind of this c value, 200.6787642. E to the kt will give me a t over 7 times ln of 5. And if I want to know what a of 0 is, I can go ahead and plug it in there. And what I get is that a of 0 gives me approximately 200.68. But let's think about this. Can we have part of a bacteria? Probably not. And if we have less than 201, but more than 200, my guess is that through all the approximations that happened, we could say, or about 200 bacteria. I don't think it's safe to say that there was about 201, even though if this was a non-application problem, we would round to 201. When it comes to parts of a living being, we round down, okay? All right, so that's our answer, 200 bacteria. Okay, so I like this problem because it showed how we had to look at ratios of the two forms of the equation that we got when we plugged in the two conditions given. This comes up a lot. Whenever we have two unknowns in a problem and it's not a linear system, this was an exponential system, this method will come in handy, okay? All right, the next topic in this section is Newton's law of cooling and warming or heating. And the model that we use is the same whether we have a cooling situation or a warming situation. So it's d big T, d little t. I kind of wish we used different letters, but we don't. Big T is temperature, little t is time. They both start with a T, so we have to leave them as is. So d big T, d little t is K, that constant of proportionality, times the difference of T and T sub m, where T sub m is an ambient temperature. And I know that people struggle with what the heck is an ambient temperature? Well, it's just the temperature around the object. But the words that some of the books use are kind of confusing. Number one, ambient temperature isn't obvious for everyone. And temperature of the medium around an object isn't clear either. But it's basically just like, what's the temperature of the room or the area where the object is. If the object is outside, then that's the temperature of the outside air. If the object is in an oven, then that's the temperature of the oven, okay? If it's in just a room sitting on a counter, then the ambient temperature is the room temperature. Okay, big T of little t is the temperature of the object at some time t that's greater than 0. All right, let's do an example so we can see how this works. A thermometer is taken from an inside room to the outside, where the air temperature is 5 degrees Fahrenheit. After 1 minute, the thermometer reads 55 degrees Fahrenheit. And after 5 minutes, it reads 30 degrees Fahrenheit. What is the initial temperature of the inside room? Okay, so let's read this again. A thermometer is taken from an inside room to the outside. So right when the thermometer leaves the inside room, it has a temperature, right? And that time equals 0, that's the temperature of the room that it was in to begin with, okay? So we don't know that value. We want to know what the temperature was at time equals 0, okay? Once we take the thermometer outside, it is now surrounded by an air temperature of 5 degrees Fahrenheit. They're telling us right there that the ambient temperature, T sub m, is equal to 5 degrees Fahrenheit. So now that the thermometer is outside in the 5 degrees, it's going to cool down because my assumption is the inside room was warmer, okay? And after 1 minute, the thermometer will read 55 degrees. Okay, so now we know T of 1 will be 55 degrees Fahrenheit. And after 5 minutes, it reads 30 degrees Fahrenheit. So it's getting colder for the thermometer. So T of 5 is equal to 30 degrees Fahrenheit. And we want to know the initial temperature of the inside room, which is that T of 0. Okay, so let's start. So first we're going to start by solving the differential equation. Okay, so we have d big T, d little t is equal to k times t minus, and now T sub m, I know what that number is. I'm going to put it in. Okay, it is a constant value. Sometimes we don't know what it is. Sometimes that's what we're trying to find, but we would leave it written as T sub n. And in our minds, we would have to remember that's a constant, okay? The only variables in here, big T, little t. T sub m is some constant that we know or we don't know. So I've plugged it in because I do know it. That way I don't have to worry about it anymore. Now to solve this, it looks like I have a separable equation again. Although, if you're brave, you could distribute the k and treat this like a linear equation. I'm going to go separable. So I separate. I get d big T over big T minus 5 is equal to k d little t. Done my separation. Now I can put my integral symbols on and I can integrate. Left-hand side, I get the natural log of the absolute value of t minus 5. Right-hand side, I get kt plus c. This should be really reminiscent of the growth and decay problems. And honestly, it really is. Temperature is very much like a growth or a decay. If you think of temperature going up as growth and temperature going down as decay, that's exactly what it is. But the difference is that there's this ambient temperature that's like this another thing that affects the temperature. Okay, not just time, but also ambient temperature. So a little bit of a difference. We go ahead and we exponentiate both sides and we get t minus 5 is e to the kt plus c, which that gets rewritten as c e to the kt. And so then finally our solution is T of t is equal to c e to the kt. Okay? So we solve the differential equation. Now apply the given conditions. So the first condition is that T of 1 is equal to 55 degrees. So that means we get 55 is equal to c e to the k. The second condition is that T of 5 is equal to 30 degrees. So that means we get 30 is equal to C e to the 5k. Okay, now I can do the exact same thing that I did before. I can go ahead and use that ratio trick. So we're going to look at the ratios. And we'll say 55 is to 30 as C e to the k is to, oh, you know what? I did this opposite. Hold on. And hold on a second. I lost something. Ugh, okay. It's not a big deal, and I'm glad that I caught it right now. I do make mistakes, and I do not go back and fix them or redo the video to fix them. I'd rather that you know I'm human. So I missed the +5. I forgot to move my 5 over. That was going to change a whole lot of things. Okay, now let's do this. T of 1 is 55, means 55 equals C e to the k plus 5, which means C e to the k is 50. Or we could even go so far as to say C is equal to 50 times e to the minus k. Okay? Now we look at T of 5 is 30. We get 30 is equal to C e to the 5k plus 5, which means C e to the 5k is equal to 25. Or we could say C is 25 e to the minus 5k. All right, now let's look at the ratios because we want to get a value for k so that we can then determine what C is, okay? If we look at the ratios, we can look at, let's see, we want to look at C. I'm going to look at these right here to go into my ratios, okay? So I want to look at the C e to the 5k is to C e to the k as 25 is to 50, all right? On the left-hand side, the c's divide out, and we're left with e to the 5k minus k, which is 4k. E to the 4k is 1/2. If we log both sides, we get 4k is equal to the natural log of 1/2, or k equals 1/4 natural log of 1/2. Okay, so we can plug that into either of our expressions for C. They both work. They are equivalent, so I'll go ahead and do that. C, let's go ahead and put an arrow that we're going to substitute it in here. C is equal to 50 e to the minus 1/4 natural log of 1/2, which gives me approximately 59.46035575. Okay, now let's see what were we being asked for? Because we've got our solution. We have T of t is C e to the kt plus 5, but we want to know what T of 0 is. Do we have enough? Okay, we know T of t is equal to the 5 plus C, which I'll leave as C, and then e to the k t, so that'll be 2 over 4 ln of t over 4 times ln of 1/2. So that means we can calculate T of 0 is 5 plus C e to the 0. Well, that's going to be 5 plus this 59.46035575, which means T of 0 is approximately 64.46 degrees Fahrenheit when we add those together. Okay, so that's saying that the room, when the thermometer was in the room, it was measuring the room temperature and it was 64.46 degrees. Okay, that's all we're after here. So let's see, this is the temperature of the inside room. All right. Sorry about the mistake in the middle there, but it's been fixed, so we should be good. All right. Mixture problems are next, and mixture problems are a bit different. The model for the mixture differential equation, they're always kind of the same. And in our book, they stress a lot of things with salt and water mixtures. We don't deal with anything else really. But the model for the mixture differential equation is dA dt equals big R sub in minus big R sub out. Big R sub in is the concentration of salt in the inflow times the input rate of brine. Brine is a salty water solution. Okay, that's it. That's all it is. The big R sub out is the concentration of salt in the outflow times the output rate of brine. And together, once the multiplication is done, what this gives us is the difference between the input rate of salt and the output rate of salt. So let's use an example to see what's going on here. We're going to do two mixture problems, one where the input and output rates of brine are equal and one where they are not equal. So this first one is where they're equal. A tank contains 200 liters of fluid in which 30 grams of salt is dissolved. Okay? You can assume that that gets stirred up. It's a well-mixed solution. Then pure water is pumped into the tank at a rate of 4 liters per minute. Okay, so pure water is being pumped in. There's no salt in pure water being pumped in, okay? It's just water, so there is an input rate. There's just no brine, right? It's all pure water. The well-mixed solution is pumped out at the same rate, which means 4 liters per minute. Find the number, A of t, of grams of salt in the tank at time t. Okay. So we got to build our differential equation. I would say that these are the more difficult application problems because you really kind of have to work to build things. Okay, first information that we're told is that the amount of salt at time 0 in the tank is 30 grams. Remember, A always represents grams of salt in this problem, okay? Now the rate in, big R sub in, that is going to be the concentration of salt in inflow times the input rate of brine. Okay, so the concentration of salt in the inflow is 0 grams per liter because it was pure water. But there is still an input rate. Even though it's not brine, there's still an input rate, and that input rate is 4 liters per minute. Notice the units that cancel are the liters. And so what I get is 0 grams per minute. Okay? The rate, or the big sub R, out. So again, we have the concentration of salt in outflow times the output rate. Okay, now the concentration of salt in the outflow, we have no idea. Okay, however, the tank has 200 liters, right? And if we know that there's pure water being pumped out at 4 liters per minute, but we're pumping out at the same rate. So that means that the tank always has 200 liters. So when we're trying to figure out the number of grams per liter, what we have is some amount of grams per 200 liters. Well, A represents the number of grams. And when we don't know, then we just call it by the variable that represents it. So this is going to be A grams, some number of grams of salt in the 200 liters. It's changing over time because we're pumping in pure water. And we're pumping out this mixture at 4 liters per minute. So now when we simplify, it's not just that the liters are going to divide out, it's that we're also going to reduce the 4 over the 200. And so what we get then is A over 50 grams per minute. Okay. I use my units, and you should use your units too anytime you're working with an application problem. Number one, because it's correct to do so, but number two, because following your units can sometimes save you in a problem. Okay, we need to set up our DE. Our DE, it says up at the top that DA, so let's do our setup, the differential equation. dA dt is R in minus R out, but R in is 0. So that means dA dt is simply negative, because 0 minus, so we get negative A over 50. Okay, well, we can integrate that. I would move the A over to the left-hand side and the dt to the right-hand side. And so this becomes dA over A is minus 1 over 50 dt, and then we can integrate both sides. Then we get the natural log of the absolute value of A is negative 1 over 50 t plus c. Exponentiating both sides, we get A of t is equal to e to the negative t over 50 plus c, and remember we rewrite that. A of t is c e to the negative t over 50. Okay, cool. We're not done yet. Because we know the initial conditions. We know that at time equals 0, there were 30 grams of salt. So we're going to use the given conditions. Or really, it's just one condition. And that was A of 0 equals 30. So that means we have 30 is C e to the 0, which means C equals 30. And our final, what are they asking for? The number A of t of grams. A of t is equal to 30 times e to the negative t over 50. This is the model. So I could pick any time now. I could pick 10 minutes, right? Pick 10 minutes, plug that in. We get that the number of grams of salt in the tank is going to be 30 times e to the negative 1/5, whatever that number is. But we would be able to calculate for any time how many grams of salt remain in the tank. And notice that that exponential has a negative in its exponent. So we've got a decreasing value of our grams of salt because pure water is being pumped in. And that's making the water a little bit less salty. All right, let's look at the next type of problem when the input and output rate of brine are not equal. I find these to be the more difficult problems, and oftentimes it's because there just really isn't a lot of explanation in a book as to why things are working the way they are. Okay, I'm going to go through all those details. A large tank is filled to capacity with 500 gallons of pure water. Okay, so right away I'm thinking, how much salt is in there? None. Okay. I'm also noticing that I have different units, gallons versus liters, so I got to work with that. Brine containing 2 pounds of salt per gallon is pumped into the tank at a rate of 5 gallons per minute. The well-mixed solution is pumped out at a faster rate of 10 gallons per minute. When is the tank empty? Okay, we got a lot going on here. The first sentence, let's see what it tells us. A large tank is filled to capacity with 500 gallons of pure water. That tells me that the number of pounds of salt in the tank at time 0 is 0 pounds. Okay. Then I want to build, remember we've got dA dt is R in minus R out, right? So we need to calculate our big sub R in, And remember, it's going to be the concentration of salt in the inflow times the rate of inflow. So the concentration is 2 pounds of salt per gallon. So 2 pounds of salt per gallon. And then it's pumped in at a rate of 5 gallons per minute. So the gallons are going to cancel out, and I will be left with, it looks like, 10 pounds per minute. All right, that's the rate at which the salt's going in there. Okay, now a little explanation here. Liquid, and in our case it's going to be brine, but we'll just call it liquid. Liquid will be going away, or I should say, it just will go away at a rate of 5 gallons per minute minus 10 gallons per minute, which is a negative 5 gallons per minute. After t minutes, what will happen is we'll have a negative 5 gallons per minute times t minutes. This is going to equal, well, the minutes are going to go away and we get negative 5 t gallons will leave. So we're finding out how many gallons leave each for, the number of minutes. If it's 1 minute, then we've lost 5 gallons. If it's 2 minutes, we've lost 10 gallons, so on and so forth. Okay? So the tank will contain 500, that's the number of gallons to begin with, minus 5t, right? So after the first minute, it loses 5 gallons. After the second minute, it's lost 10 gallons, and so on and so forth, okay? Every minute, it loses 5 gallons. So the tank will contain 500 minus 5t gallons of brine at a given time. Okay, so now we can find our big R sub out. And that is going to equal, remember, it's the concentration of salt in outflow times the rate of the outflow. All right, and so the concentration is going to be the number of pounds per gallon, right? And so that's going to be we don't know the number of pounds, it'll be some A, pounds, over the 500 minus 5t gallons. Because again, we also don't know how many gallons remain at some unknown time. Okay, so that's the concentration of salt in the outflow. The rate of the outflow we were given, it is 10 gallons per minute. Okay, and so then some things will simplify a bit. And in particular, if I think of the 10 as 2 times 5 and let the 5 simplify with what's downstairs, this is going to simplify to be 2a over 100 minus t pounds per minute. Okay, so that we've got R in, we've got R out. Now we can build the DE. This was the hard part. After this, the work is generally the same as the other problem, although it's not a separable equation. So it'll force us to review linear equations. But dA dt is r in, which is 10, minus r out, which is 2a over 100 minus t. Okay, this is a linear equation. So we want to get into standard form, and then we want to find mu, and it's not mu of x now, it's going to be mu of little t, the integrating factor. And then solve. Okay, so let's get it into the standard form. We've got, so we're going to solve the dE in this step. In standard form, we would write it as dA dt plus 2 over 100 minus t times a is equal to 10. Okay, so then P of t is equal to 2 over 100 minus t. And mu of t is equal to e raised to the integral of 2 over 100 minus t dt. The antiderivative of just a 1 over 100 minus t is going to be a natural log. So the 2 is going to be on the outside. We'll get e to the 2. That's just a constant. And then the antiderivative is actually going to be a negative natural log of the absolute value of 100 minus t. If you don't see that, then you do a u sub so that you can work through that. Okay. We want to get really comfortable with some of these antiderivatives because, as you can see, that was a minor part of this problem. Okay. Simplifying this, it becomes e to the natural log of the 100 minus t in absolute values raised to the minus 2. And then the e and the ln undo each other, and this simplifies to be 1 over 100 minus t all squared. Cool. That's our integrating factor. Multiply it through the differential equation. So we're going to multiply mu of t to the dE. We get 1 over 100 minus t all squared dA dt plus, now this is weird, when I multiply it by the next term, I end up with 2 over 100 minus t all cubed times a equals 10 over 100 minus t all squared. Okay, the stuff on the left-hand side is technically the result of a product rule of ddt of 1 over 100 minus t all squared times a. And that's equal to this 10 over 100 minus t all squared. And then we should be able to integrate both sides with respect to the same variable, dt. And we should be able to work through this. Now, really quick, I want to do something because I'm running out of paper here. So I'm going to once again do a little bit of just shrinking things up so that I have more space to continue the problem. Okay, right back where we were. Great. All right, on the left-hand side, the fundamental theorem of calculus helps us, thank goodness. We get 1 over the 100 minus t all squared a equals. On the left-hand side, that's also going to be a u substitution. And we'll go ahead and show this u sub. If we let u equal the 100 minus t, then du is equal to minus dt. So we'd have to have a negative du replace the dt. So now we're looking at the integral of -10 over u squared du when we replace everything. So this is the integral of -10 u to the -2 du. So dealing with u to the -2, I would add 1 to the exponent and divide by that. So it's u to the -1 over -1. And with the negative that's already out there, I just get 10 u to the -1, which is 1 over u. Okay, so that means that on the right-hand side, I get positive 10 over 100 minus t, that's my antiderivative, plus c. Okay, now I can solve for a. A of t, when I multiply both sides by 100 minus t all squared, I get 10 times 100 minus t, because one of them divides out with a 1 in the denominator, plus c times 100 minus t all squared. Cool. All right, so the next thing to do is I need to know c. I don't know what c was, and I need to figure out what were they asking me for anyway. Going back up to the top, a of 0 was 0, so I can use that in order to find my c. And then the question is, when is the tank empty? So let's find c, and let's find when the tank is empty. Okay, so now we're going to use the condition a of 0 equals 0. So we get 0 equals 10 times 100 plus c times 100 squared. Okay, so on the left, or sorry, on the right, 10 times 100 is 1,000. 0 is equal to 1,000. And plus c times, we get 4 zeros, so that'll be 10,000. Okay, so we have, whoops, I put 4 zeros on that first one. Should have been 3. 10 times 100 is 1,000, so I have 1,000 plus 10,000 c. Okay, so if I subtract the 1,000 and divide by 10,000, what I get then is that -1/10 is equal to c. Okay, so then a of t, let's go over here. A of t is equal to 10 times 100 minus t plus, or minus 1/10 times 100 minus t all squared. Okay, well, that's great. We've got our solution, but now when does the tank empty? In order for the tank to be empty, we would also have to be like totally out of, like there'd be nothing left, right? We're pumping in salt, so we're always going to have salt in our mixture because it says brine containing 2 pounds of salt per gallon is pumped into the tank, right? It was pure water to begin with. There was 0 salt in the beginning. And as this process goes on, we're adding more and more salt, okay? So the only way for the tank to be empty is for there to be 0 grams of salt. So when is the tank empty? When a equals 0. And we have no more salt left, okay? So that means we have to set this problem 10 times 100 minus t minus 1/10 times 100 minus t all squared. Need to set that equal to 0. Right away I can see that there's a 100 minus t in common for both. That leaves behind a 10 minus a 1/10 times 100 minus t. The 100 minus t is still there, and inside we have 10 minus 10 plus 1/10 t equals 0. And so this is telling me that 100 minus t equals 0, or 1/10 t equals 0. The 1/10 t equals 0, that's true. That's when we have 0 grams of salt. So this gives us t equals 0, and this one gives me t equals 100 minutes. Okay, so just to clarify, the t equals 100 minutes is when the tank is empty. The t equals 0 minutes is when no salt has been added. So it's kind of interesting that we get both time values, but they have different meanings. They both are saying there's no more salt, but there's no way that the t equals 0 is the correct one for us. We're looking for the time when there's no salt and no water. Everything's gone. So t equals 100 minutes is our final answer. Okay, last example is a series circuit example. And in this one, we have two first-order differential equations for series circuits. And so we need to recall some things from physics or maybe possibly learn them for the first time. We need to know what all the letters mean. The letter L represents the inductance on a circuit. R is resistance. C is capacitance. E is the voltage. I is the current. And Q is the charge. For the current, I of t, the model is the LR series circuit, so that's an inductor resistor series circuit. And we get L times di dt plus R times I equals E of t. Okay, so that's one of the models that could be used. For the charge, Q of t, the model is the RC series circuit, so it's a resistor capacitor series circuit. And that one is R dq dt plus 1 over CQ equals E of t. One more thing to remember as you work through these problems is that current I and charge, whoops, that was not spelled right, charge Q are related by I equals dq dt, okay? So let's see if we can work through an example with this. A 100 volt electromotive force is applied to an RC series circuit. Okay, before I go any further, I am dealing with an RC series circuit, so that means that the dE is R dq dt plus 1 over CQ is equal to E of t. Okay, they told me which one to use. I'm going to write it down. And they also said that we have a 100 volt electromotive force. E is voltage, and we have a volt reading. So we're being told right now that E of t is equal to 100 volts. Okay, I'm going to keep going. A 100 volt electromotive force is applied to an RC series circuit in which the resistance is 200 ohms. Okay, so big R equals 200. Ohms look like this. It's kind of a weird thing. Or you could just write out OHMS. I tend to do that instead. And the capacitance is 10 to the minus 4 farads. So big C is equal to 10 to the minus 4. And then find the charge Q of t on the capacitor if the charge at time 0 is 0. And once we've done that, find the current I of t. Okay, let's see what we got. Plug everything in. R is, okay, we're going to sub in given info. R is 200, so we have 200 dq dt plus 1 over C is 10 to the negative 4 times Q equals E of t is 100. Okay, so the 10 to the minus 4 is in a denominator right now, but we could rewrite that so that it's upstairs in a numerator. So we get 200 dq dt plus, and 10 to the 4, it's a 1 with 4 zeros. right? So we've got our 4 and then q, and that's equal to 100. Okay. The last thing to do, because this is a linear equation, we need to get into standard form. So we'll divide everything by 200 and finally have dq dt plus 50 q is equal to 1/2. Okay. All right, looking at that, I can identify that my independent variable is t, and so I need mu of t equals e to the integral of p of t dt, and p of t is 50, so I get e to the integral of 50 dt, which is just e to the 50t. So I'm going to multiply that through the ODE, multiply mu of t to the dE, and then I have e to the 50t dq dt plus 50 e to the 50t q equals 1/2 e to the 50t. Okay, on the left-hand side, this is the result of taking a product rule derivative on e to the 50t with q. And we can kind of see that, right? The derivative of e to the 50t is 50 e to the 50t times the q, that's the second term up above, plus the derivative of the second, that's the q with respect to t, that would give us an e to the 50t with dq dt. On the right-hand side, things stay the same, 1/2 e to the 50t. Okay, we have equality, so we should be able to integrate on both sides with this respect to the same integral. So I have the integral of d dt e to the 50t q dt is equal to the integral of 1/2 e to the 50t dt. On the left, the fundamental theorem of calculus steps in and the integral and derivative undo each other and leave behind e to the 50t q equals 1/100 e to the 50t plus c. Okay. Last step is to get q of t by itself. Q of t is equal to, looks like I just get a 1/100 plus c e to the negative 50t. Okay, cool. Let's see, we were told, I'm going to do a little bit of moving around here. I really wanted just this. Okay, I won't get that. All right. We were told that Q of 0 is equal to 0. The charge on the capacitor at time 0 is 0. So we're going to, I'll just do that over here. We're going to apply Q of 0 equals 0 to get C. So Q of 0 is 0. That means 0 equals 1/100 plus C e to the 0, which means C is negative 1/100. So finally, we have Q of t equals 1/100 minus 1/100 e to the negative 50t. Okay, so let me just go up. They asked us to find the charge Q of t on the capacitor if Q of 0 equals 0. Cool, we found that. That's one of our answers. The next thing they said is find the current I of t. We need to remember this right here. I of t is going to equal dq dt. So I of t is equal to dq dt. I don't go back to a differential equation. I have q sitting right in front of me. I just take the derivative of it. So we're going to look at d dt of 1/100 minus 1/100 e to the negative 50t. The derivative of 1/100 is 0, and then we get minus 1/100 times e to the negative 50t times negative 50. And that simplifies. I of t is going to equal 1/2 e to the negative 50t. So we have our current and we have our charge, and that's all that they asked for. And that's all I wrote for our notes today. We've seen several different types of application problems. If you have any questions, please reach out.